Jason, take it away.
All right, well, I'll introduce David Hertzog, who in this department mostly needs no introduction, but for the sake of any guests or young students, I'll say a few words. David Hertzog came to the department in 2010. We stole him from UIUC, Urbana-Champaign, where he was for a long time. He's been the CENPA director since 2017, and this year he was just awarded the Arthur B. McDonald Professorship of Physics in our department. So he's the first recipient of that award. So congratulations, David. He has excellent and innovative teaching, and he's dedicated his research career to precision tests of the muon. At the turn of the century, he played a central role in an experiment at BNL that found a tantalizing discrepancy between theoretical calculation and the measurement of the magnetic moment of the muon. So he started a new project to check it at Fermilab, and he essentially spearheaded the proposal, the design, the construction, the commissioning, and the first analysis of this g-2 experiment as its longtime co-spokesperson and now the analysis coordinator. So that 2-decade effort has come to fruition, and the experiment released their very first exciting results just last week, and he's going to tell us a story about it today. So without further ado, David, take it away.
Hey, thank you very much. I really appreciate that, Jason. By no means, this is a team effort, so thank you for the sweet comments about the leadership, but honestly, you just cannot do something like this project without a collection of everybody around you doing it with you. So yeah, I'm going to tell you about the first results of the experiment, and let's see if I can get this to work. There we go. There's actually been a tremendous amount of, even since last Wednesday, a tremendous amount of press. Peter Camel and his wife Eva put together a whole bunch of links you can find on our Precision Muon Physics page. If you want to understand this experiment, you could just start off by going to the APS and looking at the PhD Comics cartoon, where you will definitely learn that a muon is a heavier cousin than an electron. I like this, hey, what's up, cuz? And it goes all the way through, on and on and on. You can hear the whole measurement there. So lots of great stuff. Kind of a little bit over the top here and there, but really a lot of fun. People really enjoyed it. So first things first, let's just get it right off the bat. We determined the G factor of the muon to be this long series of digits right here. There's 12 digits here. To put that in perspective, that's how many digits you have in your credit card. And the uncertainty on that is actually at 54 parts per trillion. Now, we don't really ever say that. We say that we subtract this little piece here, we get rid of the 2. So if you take g mu and you subtract 2, that's all these digits. And then if you actually talk about what we call the anomaly, so you'll hear me say this a mu or g-2 over 2, that's actually just g-2 over 2, the piece above there divided by 2. And that's the number that we typically do report, because that's what the experiment is sensitive to. It's sensitive to the stuff in the blue bracket there. So the relevant scale for today is just, if you want to remember one number, is keep in mind, I'll tell you lots of things that have uncertainties, and this is an uncertainty kind of business. So the uncertainty of this first measurement by us is 460 part per billion net uncertainty. And so I will show you various effects that have uncertainties in that unit of part per billion. Okay, so again, this is a team effort. There's 200 people, there's 35 institutions, there's 7 countries. It's taken us about 11 years to do this. Because we're here at the University of Washington and we had such a major role in this, I'm going to take a couple of minutes right now to tell you about this massive effort by lots of people here. So in fact, across the top, we have the graduate students here, starting sort of in semi-chronological order here. This is Nathan Fromig. The first 4 have all finished their PhDs. Nathan came along rather bravely when this was a young project, not so certain. He went off to Brookhaven and brought the magnet back with a few other people. And he got his PhD in accelerator physics. He actually developed a lot of the beamline designs. He was the one person that could really tune it, a lot of the software and so on. And he went into that field for a bit. This is Matthias Smith. He basically got involved early on in the magnetic field side of the thing. And along with Rachel and Matthias, they worked on things like shimming the magnet, developing that and doing the early analysis of that. I'll just jump to Rachel right now, since I said the magnet. Here she has her with her head sort of stuck halfway in the magnet. In fact, Rachel did one of the first analysis of the field. And we always talk about the radial field measurement is always Rachel's radial field. And that's sort of a lingo that sticks. Here's Aaron Feinberg. A lot of you knew Aaron. He started at the beginning a little bit more on the detector and precession side of things. He was, he and I and Yark and others were finding out what is a lead fluoride crystal, what is a SIPM from scratch and bringing it up. But Aaron's kind of known for what, beside many, many things he did, for what he did to develop the analysis protocol, which is sort of called the Recon West. We're out here in the West, and that was one of the primary things that many, many analysis groups used. He's now at Penn State. This is Jason. He came along and finding out that we wanted to build these detectors, but they weren't really built. And so he sort of took over in the hardware side of detectors, building all the detectors, installing them, running, spending time a year running the experiment. And you'll see a little animation of him later. Hannah started off building a little detector system here, which you'll see a little bit later. And she went on to do a lot of stuff on the online software. And one of the most critical systematics, has her name written entirely upon it, which you'll tumble into later. This is Bryn. She also, along with Peter Campbell, they developed a really exquisite set of complex detectors that profile the beam on the way in the door. And then she also led one of the major things in the analysis that I'm going to report today. And then Josh came along after some of this done, wondering what he possibly could do, but now he has more to do than anybody could ever imagine. He's running all kinds of things in the experiment, from computers, analysis, calibration, and so on. He's actually spent the last 2 months helping design a completely different experiment with Peter and me. Some postdocs are here. This is Kim Shang Ka. This is Martin Fertile. Both of them are now professors of their own right and running their own G-2 groups. This is Zach. He's joined about a year ago. He's at Fermilab, and he's basically helping run the thing with Yarek. Down here, some more senior people. There's Alejandro, myself, and Peter. And of course, Yarek Kasper, I always call him Scotty in the engine room of Star Trek, because there's not a darn thing that ever is broken, busted, or whatever, in which they don't call Yarek in to get it to work again. Eric, who did a lot of stuff with the magnetic field and figured out one of the systematics as well. And then here's our group enjoying some time in Elbow when we thought we were actually going to release the number. That's so long ago, and how naive we were about how hard it is to do that. Of course, there are lots of undergraduates who helped us, and the CENPA staff. We would not even be here without the fact that CENPA has supported all the construction of things: machinists, detectors, electronics, engineering, and mechanical designs. So that was my little reminder, and I'm sure I even underrepresented all of the work right there in that pitch. So back to some serious stuff now. The muon's anomalous magnetic moment, I told you, is what we also call G-2/2. And that G factor is just the ratio between the magnetic moment and the spin for a particle. And long ago, Dirac realized that if G should be exactly equal to 2 for a point-like spin 1/2 fermion, like an electron. Now, then it wasn't so long later, decades later, we realized, hey, a particle with a spin 1/2, like a proton, has a really big magnetic moment, a big G factor. And so, it has what they call an anomalous part of the magnetic moment. And that can come from internal structure. So all of the baryons have big magnetic moments, and a neutron has a big magnetic moment, even though it doesn't even have a charge. It has a 0 right here. But also for point-like particles like an electron or a muon, you're going to pick up an anomalous magnetic moment from virtual loops that encapsulate all the possible interactions in the quantum vacuum. So that's kind of what we're talking about here. And what we call the G-2 test is if you can compare a measurement to a very precise calculation of that anomalous part to investigate whether the standard model is actually complete. And that's what we want to do. So we have to start off by asking ourselves, well, is the standard model, how well is it predicted? How complete is it right at this point? So let's take a real brief tour through that and start off by going back to around 1947, where the first deviations from that Dirac picture of G=2 were starting to be realized at about the 0.1% level. And so they were observed for this point-like electrons, and this led to the development of quantum electrodynamics. And everybody loves this thing, and we can all calculate this from our courses in graduate school, where we can figure out the first leading term, the so-called Schwinger diagram here. So in these pictures you're going to see, you'll see something like on a chalkboard here, you're going to see a muon line interacting with a magnetic field here, and then the exchange of something like a photon here. Okay, and that first coefficient is just alpha over 2 pi. It's about 1 over 858 or so. And it's so important that these are the kinds of things that you put on your gravestone. So of course, QED is incredibly precise. It's our most precise theory, and over decades, it has reached extraordinary precision, mostly pushed to do the electron. In fact, we know this out to such a level that I'm going to write down here a few times. You'll see in blue coming up in the next few slides. The takeaway is it's totally negligible, the uncertainty. We know this way, way better than we could ever require it in a g-2 measurement, but not so for the electron, but for the muon. So you can also say, well, if you have a photon diagram and you believe in the unified electroweak theory, you can replace a gamma, an exchanged photon with an exchanged Z. So this is the Schwinger term with a Z in it, if you want. And this is a complementary term with a charge W in it. And that's just the weak interaction terms. And because these guys are heavy, the W and Z, they come at a much, much smaller level, but they're calculable by perturbative effects in the same way. And the uncertainty on this is, again, totally negligible. Now let's get into the bad stuff. So the difficult diagrams always involve hadrons. They always involve quantum chromodynamic problems because you cannot use perturbative calculations to do those sort of loop diagrams. So here we have our familiar diagram again. And if this was a QED diagram, you would see this as an E plus, E minus, and you would call this a vacuum polarization insert diagram like that. But just as well that this is a 1 minus quantum number here, it can make a vector like quantum, it can connect to a pi state like this, or anything else that connect in here that's hadronic. And now you cannot calculate this. This is a mess. So people have to come up with a tool for that. And then what's really been nasty and plagued the experiments for the last 15 or 20 years is this next higher order diagram where you have all these little tadpoles connecting into the muon line here and some pseudoscalars running across, things like this. This is called hadronic light by light. So again, you can have a light by light QED diagram. This is hadronic light by light. And this became very, very difficult to deal with. So this was always done with models from sort of what hadronic models that looked like kind of old school things that had a little bit of this and a little bit of that in them. And nobody really believed that. So in the old experiment, it was always difficult because the old experiment seemed to differ from theory. People thought it's got to be this thing. Now, in both cases now, we have data-driven versions of this, not model-driven. And I'd like to highlight my colleague and good friend, Martin Hofdirektor's work. He was here at UW for 5 years, I guess, as an INT fellow. And during that time, he and these collaborators in some of these papers here developed an unprecedented calculational technique to deal with this diagram from data. So it's very hard to read, but in the end of the day, this diagram, the uncertainty on this diagram has almost disappeared in terms of the relevance right now and get better. So in fact, it's about 154 parts per billion, keeping that in mind. Now, the real thing is, what about this diagram? So this is the biggest contribution with the biggest uncertainty in the standard model calculation. It's called hadronic vacuum polarization. And how do you get it? You get it from decades of precise E plus E minus experiments who measure absolute cross sections, and then the simple dispersion relation here, which relies on analyticity and the optical theorem. So very solid ground, no controversy that this little recipe, if you measure them. And I'd like to at least show you briefly how that works. So if you take a diagram like this thing, and you get out a pair of scissors, and you cut this diagram in half, then you've got the piece from here inserted right here. So here's that little virtual photon going to 2 pions. Now, how do you make that thing? You can connect that now with an insert here, E plus E minus, where you know what that vertex is. So now you've isolated the piece you want to know, and so that eventually turns into E plus E minus goes to hadrons over muons, calculations over all kinematically allowed channels and energies. And the most important by far is this yellow stuff here, which is essentially what I drew here, the pi channel. So many, many people add this up, and it's become kind of an industry to do that. The takeaway here is the uncertainty dominates the standard model, and it's at 340 parts per billion. So you might remember that that's the bigger one. Okay. Oh, I forgot to tell my clock that. Okay. So the way this finally started to get organized was the formation of the so-called Muon G-2 theory initiative. And they've been meeting for, I don't know, 4 or 5 years now in different places. And the idea was for them to develop the benchmark value that the collaboration could use and to publish that all the time in advance of a release by our collaboration. And they have done that. And the last meeting was here in September 2019. Here we are in front of the fountain. A few of us organized this, and we ended up with this nearly 200-page physics report with all of the participants around the world who contribute to what turns out to be the benchmark value right now for the standard model. And that's what the collaboration will use. And if in 2 years from now, this number changes because of additional information, new calculations, new data, that's what we'll compare to the next time. That's all we can do, is have some kind of a plan like that. And we don't want to pick and choose because there are other individual results floating around. And that just doesn't seem, that seems too arbitrary. Okay, the takeaway, interestingly enough, is that the combined standard model uncertainty is 358 part per billion. And let me just to give you a hint, when I take the new measurement that we do plus the old measurement and average them, it has exactly the same uncertainty. So this is just to remind people where things were. This is not new information. This was the old experiment about 20 years ago. The data was taken. And this, the present, if you had to run out as of a few weeks ago and say, where's G-2, you would say it's more than 3 standard deviations away from the updated standard model value, which is not too far moved, but on much, much firmer grounds based on the calculations and the things that I mentioned. So let's talk about a little bit later what this might mean, because right now G-2 is kind of uncomfortably lonely in the search of the crack of a standard model. We'll come back to it sort of at the end rather than me try to interpret anything for you. Because I'd really like to spend the time to tell you about this new measurement. And here's the collaboration again, meeting in front of the fountain. Unlike the theorists, we did it on a sunny day, they did it on a rainy day. And the thing I need to tell people about this collaboration is just how broad it is in terms of its talent. Particle physics, nuclear physicists, atomic physicists, optical physicists, actually accelerator teams, and actually several theorists who run shifts and do things with us. But we're all sort of aiming to do G-2 together, and the ultimate aim of the experiment is 140 part per billion. So I'm just telling you about the first scratch of data we're able to analyze. This would require 20 times as much data as was obtained in the entire time that we ran the experiment at Brookhaven. So it's quite a challenge. So the reason you can understand that this is quite a diverse experiment physics-wise is because actually we just did something kind of extraordinary as well, which is on the day of the release, we literally had these 3 out of 4 of our major papers published, and this one will be tomorrow. We're just finishing the proofs of this. One in the PhysRev letter, which is on the cover, the Physical Review D, which is sort of the domain of particle physics, the PhysRev A, which is about all of the magnetic field measuring techniques and atomic techniques, and the Physical Review AB, accelerators and beams, which is all of the beam dynamics and the systematics and the complicated corrections that go into this. So this has apparently never been done before. There's at least 100 pages for you to read if you don't like this talk. So the fundamental experimental principle has been the same for decades in terms of storage ring experiments. You basically determine the difference between the spin precession frequency and the cyclotron frequency for a muon that's moving in a magnetic field. So for example, we introduce muons into the ring. Here's the ring. And as they go around, their momentum vector is this black vector, is always going in the direction around the ring. The spin vector, let us say that is polarized when it comes in. So let us say for the moment, it's in the same direction. As that muon goes around, the spin vector slightly advances with respect to the momentum vector, such that every 29 times around the ring, that red vector goes an extra lap. That's sort of exactly the order of magnitude of this. It's a slow advance. And that is what that difference frequency is between the spin and the cyclotron frequency is what we call the anomalous precession frequency. This omega A you will see a number of times. And it's simply proportional, which is beautiful, to A mu, the anomaly, and the magnetic field. So that if you can measure this precession frequency, and you can equally well measure the magnetic field in which the muons have been swimming, then you get the anomaly bang by long division. As Paul Debevec used to say, and then we do long division. But it's a little bit more complicated than that, because you could never just put muons in and have them sail around inside a magnet. We all know that they would go into the ring with a vertical divergence and other aspects and never be stored for more than a few turns before they slide away. So we have to introduce a storage mechanism, and it can't be a change in the magnetic field. It can't be magnetic focusing. So we use electric focusing. Electric focusing means we use quadrupoles, and the quadrupoles introduce an interesting new effect, which I'm going to show you how we minimize. So basically, the idea, and this came up in the mid-70s for this kind of experiment, is if you can run the experiment at a particular momentum, this third term here in the expression for omega A goes to 0. They call this the magic gamma at 3.094 GeV over C. This term just is well known enough that it goes to 0. And you're talking right here about what's called emotional magnetic field. So if you imagine the particle going in, I'll show you a picture of this later, but the particle going in its direction, cross it into a radial pointing electric field, put your thumb up, you'll get a vertical magnetic field, and that's why that would change this, this precession. It does, the particles also go up and down between the plates of this, and that is, if it's out of plane, you get what's called a pitch correction, which is going to come. So both of these are going to come along a little bit later again. I just want to alert you to the idea that we try to minimize them, but they're still there for a correction. So at this point, we could pause, and I always like to remind myself of the way Francis Farley, one of the real primary people who invented all of this storage ring ideas decades and decades ago. He's now passed at nearly 100 years old. He used to say there are 4 miracles that permit us to measure G-2 to sub-part per million precision. First of all, from nature, we get polarized muons. I told you you need them polarized. That's often hard to do. They come for free in pion decay, just by the helicity conservation in the back-to-back decay here, in the handedness of neutrinos. We got 97% polarized in the forward direction, so we can't even have them unpolarized if we wanted them. They're coming polarized. The next thing is the anomalous spin precession frequency is proportional to G-2. I mentioned it here. It's mentioned to proportional to G-2, and it's not proportional to the momentum. You do not need to know it exactly how fast they're going. You just put them in and it happens like that. Then at that magic momentum, the electric holding field does not perturb the spin frequency. So that was a beautiful idea. And then the final thing is, how do you know which way the spin is to know which way it's turning or how fast it's turning? Once again, parity violation enters the game, and the parity violation reveals the spin direction by encoding in the energy spectrum of the positrons this kind of modulation, which you're going to see a few more times in various manifestations here. Okay. So now let's get a little bit more technical. This is actually the expression you will see in the paper that we use to come up with the anomaly. And the stuff we measure over here is that precession frequency. And downstairs here is a complicated thing I'm going to come back to, which encodes a lot of information about the magnetic field. In order to do this and get it in the right units, because this is related to the muon, and this is related to the co-magnetometer called the proton here, we have to do some conversion things between protons and electrons, bound and muons to electrons, and so on. And all of those factors, we call them the fundamental factors. They're known very, very well. They're known better than we need to know them, at least right now. And so we acknowledge all of those in a fine way. So recall, we're going to be measuring 2 frequencies and dividing 2 frequencies. This is a good thing to do in precision physics because you can measure frequencies very well with precision clocks. So how do we get those polarized muons? This is the Fermilab campus, part of the Fermilab campus looking down, and it goes like this. Thanks to Bryn, you basically have a batch of HEV protons running around the recycler ring. They divide those with a lot of RF frequencies into 4 small bunches. Each bunch comes around one by one, smacks into a target that used to make antiprotons a long time ago when our D0 group used this. And then this distance from here to about here is nearly 280 meters. And in that amount of time, most of these yellow pions have decayed. Now they become blue pions. have decayed into muons, and there they are. And the muons, we send them running around this track, which used to run and save antiprotons, and then into our storage ring here. There's lots of reasons for all of this if you want to ask me for this later, but it's not important for now. So once they come into the room, the hall in which the magnet is sitting, they have to pass through these last quadrupoles here. A lot of this design was done in the timing of this by Nathan. And then they pass through the detectors built by Hannah here and by Bryn here as we image them coming in the door through an interesting magnet called an inflector, which I'm not showing here, which makes a field-free region. They come along and then they pass through these plates in which there's a gigantic pulse of current that gets sloshed in and out in the way that you see in this black thing here. This is the current, which produces a very strong magnetic field of the order of 280 Gauss. This thing had problems originally, which some of our guys came along like Yarrick to help fix. But what it does is it puts on a little transient field right there. You see it down and then away. And by what that does is gives an outward kick to the muons so that it aligns this incoming red orbit onto a stable green orbit here, just by kicking the muons out. So it's very fundamental to get things into the ring and stored. The next thing is to keep them there. And I mentioned to you that there was a quadrupoles, electric fields, in these regions that are painted here in yellow are these devices which are photographed here. You see the plate, 1, 2, 3, 4 plates of a quadrupole, which sort of makes this whole thing a gigantic penning trap. And so by putting a positive voltage on the top and bottom plates here, anytime a positive muon goes up or down, it's pushed down. So it's focused down and it's defocused this way, but the magnetic field keeps it in play. And normally what we do is we turn these things on every time we inject muons into the ring. We turn these quadrupoles on with an RC time constant, just the standard thing you're used to in that kind of a lab, of about 5 microseconds, and then it should be stable. So it comes up well enough in advance so that the voltages are stable and keeps things stored. However, the big problem that we found after we took this data was that 2 out of 32 of the high voltage resistors that ended up not having 5 microseconds, but had something more like 100 microseconds. They're drawn here and it's in the paper. So that meant that 2 of these plates were coming along way too slow, and it cost us a lot of time because it meant the fill was unstable during the storage period. The electric field was not quite stable in this one region over here, and that basically meant that the beam moved a little bit, and I'll come back to what that cost us in terms of an effort. Hey, you're inside the ring right now. Take a ride. So if you're a muon and you're zooming along on an amusement park, this is what you would see running around. You'd see plates, you'd see straw detectors, you'd see all kinds of plumbing and things at various places and ports. And if you're a muon and you decay along the way, you'll spit out in this same direction you went a positron, which will go forward, and then it will curl to the inside because it will have a momentum that's lower than the momentum of the muon, and it'll strike one of the detectors we're going to see in a few minutes. So actually, so if you imagine being in that ring right now and going around, what does it really look like if you could just have the tomography to image that? So if you had well, we do have the tomography to image that because the straw detectors allow us to create a picture of the intensity distribution following an injection. So you're actually watching time since the injection in microseconds. And this is really what's happening. The beam is moving back and forth like that. It's oscillating with a characteristic frequency in both the width and the mean of this frequency, which is related to the voltages that you put on those quadrupoles. And this is the weak focusing condition. And this is what you're seeing there is a manifestation of what we call the betatron frequencies. The betatron frequencies, and then this is actually modulated against the cyclotron frequency itself. The static image of that is very important. We do need to know what the average distribution is. It looks kind of like this avocado plot here. This is not ideal, by the way. We want the intensity of this to be where X marks the spot here. And that could only happen, it happens now, by improving the kicker. Stronger kick, you could put the beam in the middle. We were unable to do that in run 1. Okay, more stuff on this ring. And so actually all of the instrumentation around here, the 24 electromagnetic calorimeters, they were all built here at UW. And then what you can't see, but all the way around in the same sort of locations, are 378 pulsed NMR probes also built here above and below the vacuum chambers. So the detectors look all a little bit like this. And we're going to watch Jason sort of do a little bit of wiring here in the last bit. He did these time-lapse and photography of him creating a lot of these things. I think it would take him typically all day long to, from scratch, build an entire detector, and then it had to go through all the checkout procedures and so on. So one by one, we built these. And then down here is sort of one of the brand new probes that was designed here at CENPA by Martin Fertile and built by a lot of our undergraduates and a team, and Eric Swanson helping design this and test these. Eric built all the electronics for this, and with CENPA engineers. So all of that was sort of two of the major things that are in this experiment. So if we take a look for a moment now at the calorimeters again, by the way, this is Rachel all the time when you see this picture. The calorimeters are everywhere here. So if you take a picture of one of them, each one of them has a chariot here full of electronics and lots of other services. And the business end of it is in the nose right here, which sticks itself into the magnet. So that's why it has this funny shape. The positron curls to the inside because it has lower momentum and it strikes this thing. This thing is basically a calorimeter, which is made out of 54 beautiful lead fluoride crystals. They're all shrink-off detectors. And all of this electronics and these silicon photomultiplier electronics and all of this was like this, all designed and built here. So each one of those gives a very fast pulse. On the time scale, you can't quite see here. This is up and down. This pulse represents the energy of a positron in here, and the width of this is literally about 8 nanoseconds or something, and they can run at incredibly high rates. So we get this kind of information. The raw data rate that we flow through this thing is something like 25 gigabytes per second of raw data that has to be processed very fast into these islands. And then what you want to understand is as the spin goes around, this is the spin vector, and this is the momentum vector, the positrons that arrive in these detectors in terms of rate vary with this frequency here. This is the energy of the positron, and we get more than when it's lined up, fewer when it's back, more lined up, fewer when it's back, and that is the modulation you see. And we collect those with an energy threshold, put them into a histogram, and the histogram starts to build here. So this is a real-time histogram, and this is just showing how fast it builds up in 10 minutes so far. Now, we have to take a lot of data because we have to run for years and years. So we're not going to watch this for years and years. But this is how this famous, what we call wiggle plot, gets assembled. The pulse has to be large. The modulation of this is based on the spin orientation, and then it goes into the histogram that we fit. So many people have heard this story. The magnet was moved from Brookhaven. Then it was reassembled. It was pretty tricky, took a long time. And then we had to turn it into something that was an instrument for scientific investigation, meaning in this region here of 9 centimeter diameter, the magnetic field team had to create an incredibly uniform field, because if it's not uniform, this directly makes the analysis difficult. And so there's lots of tools for the physical magnet itself, all of the things listed here. There's yokes and poles and wedges and top hats and shims and surface coils. All of this was well known from Brookhaven. And the Brookhaven uncertainty in the end was this wiggly blue line here. And what the axis here is 0 to 360 degrees. So imagine you're looking at part per million uniformity bouncing around the ring. And we achieved the exact same thing until we came up with the last step, which is written in red here, where we used 8,000, not ERFIS, but surface iron foils, which could change the effective mu locally. I'll show you a picture of that on the next page, but I want you to see the animation of this invention. So all of a sudden, by installing these things, in testing it, this red is our magnet, and it became, bang, 3 times more uniform than Brookhaven. And this was a big improvement. And this was a lot of work by many, many people, many of them in our group and other groups. Okay, so what are those things? Those things were all actually cut at the CENPA laser machine here, something like 8,000 tiny iron laminations. They were all sent to Fermilab, where they were weighed and sorted. And then as we measured the field and knew where it had to go, here's Eric and Brendan. They're building basically templates. These templates had to be glued above and below all the way around the ring until we did the stuff that you saw before. So that was a big breakthrough. So how would we know what to do? The way we knew what to do is we're using the tomography available of having a chariot full of NMR probes, pulse proton NMR probes. So in a magnetic field, you kick the spin over, it does what we call a free induction decay. In a very uniform magnet, you would see a free induction decay that can actually be quite long here. If it has a gradient field, then it has this funky look like that. So what we do is we basically, first we had a shimming trolley with 25 elements. And this is a nice animation from Matthias, so I just like to use it still. And essentially, as you go all the way around with 25 of these probes on the front of a bus, essentially, go around the ring, like the dot is going around the ring here. At each place, you can see places that are not uniform, and you can get the magnitude of the field, and you're plotting it here as you go around. And from that, you iteratively go back and improve the shimming. Now, we have a similar item that Peter Winter's group at Argonne has really upgraded and developed, where in now what we use when the vacuum chambers are in, we can no longer use this device. This object has 17 of these probes, and we use this all the time to go around to map the field and its magnetic multiples about every 3 days. Now, what we do in between is above and below in these little orange spots where there's this trolley with 17 probes, is we monitor the field 24/7 all the time with the fixed probes. So we have all of these tools to measure and monitor magnetic fields. Okay, so run one data taking was, you just commissioned the experiment. You're still trying to figure out what to do. We ended up breaking it into about 4 analysis periods based on the way the kicker was used and what kind of voltages we used on those quadrupoles. So that all constituted run one, and it was broken in. Sometimes you'll see 4 data sets, but I'm just going to give you the combined results, which are fine. Okay, there's always problems. First of all, the temperature of the hull was wacky during the whole thing. It was going up and down like that, and what that did was change the magnetic field in a nasty way. I'll show you. The kicker had, the first installation of the kicker was sparking and crashing. It limited what we could do. And 2 out of 32 of the resistors were just made homemade like this because the company didn't supply the professional ones, enough of them. And so all of that cost us some serious problems. The magnetic field team had to literally track the magnetic field over something like 60 or 70 hours here as it changed by a tremendous amount compared to what we actually want. Now they've got tools to do it, but it was dynamic. The kicker was not good enough, so the beam wasn't parked in the center. And these bad resistors meant what we call the optical lattice here should be stable early and late, but the green and the black curves are not as you go around the ring. And some of that frequency I told you about when things sloshed back and forth wasn't constant. It changed, and we had to accommodate that in all of our fits. So all of this is resolved. So one of the great things you can say is none of this is true now. Okay, I'm going to take a breather. I know I've been ripping pretty fast. I know that you're probably going, whoa, at this point. And I think I'm now going to tell you about how we analyze the data. So now you're really going to go, whoa, because this was a big job. And I like this phrase because it really lets you know how we approach things. Everything that we did that was important was done with multiple analysis teams on every effort, sometimes up to 6 teams, 2 teams, 3 teams, and kept as independent as we could. Calibrations, alignments, calibrations, constantly. They never get credit for this in the background as they do the detailed levels of keeping detectors the same game, knowing where tracker detectors are and how they're lined up. All these things are super important. The relatively blind analyses of the intermediate folks was even done. So if 2 teams didn't work at the same thing, they worked blind from each other until they really felt it was time to compare. And there are many specialized systematic measurements were done, campaigns that were done just to figure out a certain number, some of them with no beam and some of them with beam. And I think this is kind of impressive. I looked at our document database, so-called DocDB, where we enter everything since we began assembling the experiment and building it. We have 25,000 documents in this database. And I assure you, I have by no means read all of these documents. So if you looked at my CENPA whiteboard about a year or so ago, you would see that the sketch that I sketched one night, I had this thing in my head and I went in and I basically sketched the entire analysis plan of all of the different teams we were trying to keep track of. And it kind of looked like this, and it was sort of fun, and the collaboration kind of got a kick out of this. And this actually turned out to be right, by the way, it never really changed. You might notice right here, the proverbial elephant in the room. And the elephant in the room, way back then, we had identified one big problem that was going to be nasty for us. And not too long later, a second elephant came along. And the reason that we're not published this data a year ago is there were two elephants, and each elephant had their day. Let's just put it that way. Let's be a little bit more professional than that, no. And now the master formula for the analysis actually looks like this. So there's many measurements that determine a mu. And I want you to walk through, I'm going to walk through these terms, knowing that the two elephants are going to get their moment at the end a little bit here. They're in blue. And just to let you know what these things are briefly, this is the blinded clock frequency. Omega A with the M is what we measure in the precession frequency. These four things that come next are all corrections from the electric field, the pitch, something we call muon loss, and a phase acceptance. These additive small corrections convert this measured frequency into the one you actually need in the formula. And then on the bottom side, F calib is indicative of the fact that we have to turn the magnetic field proxy measurements we do with the protons into absolute fields. And then we have to measure the fields in space, and this is x, y, and then as you move around, I'll tell you what the prime means later. And the m is where are the muons during that time. And then finally, there are two more corrections. One is a kicker transient, and one is a quadrupole transient that come along that slightly alter this. So we basically have a numerator here, which gets us this correctly, and a denominator there, which gets us the profile of the beam in the magnetic field glued together like that. So let's get started. Okay, we start with the easy one, which is the clock, which everyone loves so much. So the clock is just basically a very GPS disciplined master clock. There's a lot more hardware than this. It's all behind locked cabinets. The only people who've ever touched this are Greg Bach and Joe Lycan, who's basically, they're not in our collaboration. They're Fermilab management, and they write down whatever frequency they run this thing at, plus or minus about 25 ppm around some target, so that we think we're pretty good to know how fast our clock runs. And they write it down and they put it in these envelopes here. Some of them are stored here in Seattle, and some of them are stored in Fermilab, and that's just in case there's an earthquake in one place or another. We wanted them far apart. Okay, the bottom line, by the way, you're going to see at the bottom, like takeaway here, uncertainty 0. Then I just want to flash this thing because our Italian colleagues have built the most. This is the Italian Optical Institute, guided by Graziano and others, this exquisite laser hut full of lasers and tons of optics, so that every single one of the 1,300 crystals was able to get calibrated brilliantly all the way through. So we know the gains. Secondly, another thing to say in terms of the raw data is, before you build the wiggle histogram, is the corrections that people had to do to remove pileup. If two positrons run into the detector at the same time, they add up enough energy to look like a different positron. And this red one versus this blue one, the phase is different, because if you were a muon here, but you didn't decay until here, your spin would turn that much more. And so this is an important correction to get right. And we know we get that right when you look at the following. This is a log scale versus energy. 3.1 GeV is the maximum energy. So the right thing is something that goes down here and stops. But what you get originally is something that goes out here, because this does happen. So we have multiple correction routines that were built to take care of that. That's just a short shout out to the people that do those reconstruction efforts. Now, to get the measured frequency, this omega AM, like that, you get that wiggle plot, and you would typically just fit that with a 5-parameter function. So there's a normalization and an exponential decay, and you see an amplitude of the wiggle, modulation, you see a frequency and a phase constant. But this is incomplete. If you fit that, and then you look at the Fourier transform of the residuals, you get all of these peaks. So where did they come from? Well, of course, they come from that very thing I showed you in the movie, which is that the beam is moving back and forth. And because it's moving back and forth, that modulates the acceptance of the detectors. And so it modulates this otherwise simple formula. But by the time you're done putting everything in here, it gets to be pretty complicated. The other thing that happens is occasionally a muon will leave the ring. And when they leave the ring, these are 3.1 GeV muons, they punch through 3 detectors in a row, which makes a beautiful signal. So we know exactly how many there are. And we have to take care of that. And when we build those 2 things in, that's the slow factor here. This is the fast factors here. When we do that, we end up with a very complicated fit function, but we end up with perfectly good residuals. So this black here represents that we have absolutely structureless residuals, no slow terms, no peaks, nothing when we're done. And the chi-squared on a fit like this is perfectly compatible with 1. So that is the necessary but not sufficient condition for a good fit. You have to start there, and everything's like that. So just to give you a flash, there are lots of analyzers, like 11 different kinds of analyses. The result doesn't depend on when you start the fit. The result doesn't depend on which calorimeter you used. The result doesn't depend on which one of the many analyzers or different techniques that the analyzers employed used. The result doesn't depend on what energy bin you used. So we went through, obviously, years of checking this stuff. But this is the largest uncertainty is just statistical. We just have 434 out of that 460 is statistical. The systematics is already beating our error budget, which is amazing. So the instrumentation that was developed for the experiment is pretty extraordinary. Okay, so now let's move to the denominator briefly here and talk about this prime. So we encode this whole denominator term in red as omega p prime tilde at t sub r. So what is the prime? The prime stands for the proton NMR calibrated to a shielded, what they call the shielded proton, equivalent precession frequency of a proton shielded in a spherical sample of water at this 34.7 degree reference temperature. By the way, this number is what our speaker coming up, I just drew a blank, very soon, I'll tell you in a second, is our Nobel laureate speaker, Bill Phillips. This is Bill Phillips's thesis that takes you back. The tilde decorating on top of this thing, the tilde is telling us the stuff about the fact that we merged this with the muon distribution. So the steps to obtain this quantity, you first have to have an absolute field calibration, which we do with multiple absolute field probes, spherical, cylindrical, the one from Brookhaven, and a brand new one built at Michigan with helium-3 probe. So we have lots of ways to know that we know what a Gauss is, let's say. Then we have periodic in-ring mapping of the field multiples as we go around with the trolley, and we measure when the muons are not there about every 3 days. Then we have continuous monitoring when the muons aren't in the ring, and that is basically, let me check my time there, continuously monitor where the muons are, and then we fold those together. And so the uncertainties of these are very, very under control. So again, here's that picture of a trolley. Here's the multiples as they go around. The trolley maps are done every few days. We have to go from a point here where we have a trolley to a point here we have a trolley. And so we track the magnetic field in between using the fixed probes. And then we use a random walk process tied to each end, which is called a Brownian bridge, to know what the uncertainties are along the way. In the end of the day, this plot that Bryn made for the PRL is essentially the folding now of the field with the muon distribution, which gives us that denominator. So let me, real quick, the corrections. One of these known, these are the first 2 are known for a long time. Imagine if you're a muon, you go through this radial field here. This term becomes non-zero slightly. We have to measure that. We measure that by knowing the distribution of the muon radii here. This is the momentum distribution, or equivalently the radial distribution of the stored muons. You plug these numbers in, it's plug and chug. It's a big correction. It's big because we didn't center the beam, but it will always be there, but it's known very, very well. And we're working on this one going forward to make that smaller. Similarly, the pitch correction, because you're going kind of up and down as you're being focused, is a straightforward correction that you just need to know with the trackers what the amplitude of that is. And you can see the uncertainty on that correction is down to 13 part per billion. It's almost negligible. It's not a small correction, but we know it very, very well. Then we end up with two things that were not expected, and these are a little bit related to this word phase, and give me a moment here, because you might like the physics of this, I think you'll like the physics of this. So here's that nominal 5-parameter function with a phase constant. But what if the phase is not constant? What does even the phase mean? The phase is the average spin direction of the ensemble of the muons at t equals 0. So that's the physical meaning of that, of the ensemble at t equals 0. So, but if that was changed as a function of time and you do a Taylor expansion, then this omega t has now picks up a phi prime time t, omega a plus phi prime t. These two together become omega a prime, and omega a prime is now not equal to omega a. You got the wrong number. So this is, there's no really important physical meaning that phi, there's no matter what the value is, it just has to be constant like that. So here's two things. One of these was alerted to us. Aaron Feinberg and I started worrying about this, and Aaron calculated his thesis that this thing could be really bad if some of the muons that were lost during the storage all had the same spin direction at t equals 0, and it was different from the rest of them. So Hannah and Yark and others developed an idea to basically first measure whether there was a correlation of momentum to phase, and sure enough there is. It's exactly equal to the calculation. It's quite large. We did a big trick to do this, which I won't explain more. And then we did some special runs that Yark cooked up in order to load the ring with either mostly high energy muons and then only mostly low energy muons and some things in between. And then Hannah figured out the correlation between how fast each high energy muons left the ring versus low energy muons. So that's dp dt of a muon loss. This is d phi dp of muons coming in. You fold those together, and fortunately, they're balanced enough that this turned out to be pretty small. We were afraid this was going to be more than 10 times larger, and then we had no idea originally how to figure it out. We did a data-driven thing. We wiped it out. That was a big success. The last nasty thing, this elephant is so big it cost us 1.5 years of our lives. This is the nastiest of all of the elephants. So first, there's a fact of life, and the fact of life is versus the decay position inside the ring, where the wiggle plot occurs has a different phase. In other words, it may be pointing more inward or not inward, depending on how vertical you are. That's perfectly okay, because you can sum up cosines of the same frequency in different phase, and you end up at the same cosine frequency. That's perfectly fine. And so, but if the distribution moved up and down, which we see it does, we see that the distribution squeezed a little, like this, on each fill. Load it, squeeze, load it, squeeze, like this. And so that introduced a phase shift, which is indicated here. And that phase shift then got folded into the fitting process, and we had to figure out what the perturbation was from that. This is a totally trivial explanation of an effect that's quite large, but it leads for a pretty big correction and a pretty big uncertainty. The good news is this will never happen as soon as the resistors were replaced with correct resistors, this essentially goes away. So we just had to suffer for this for run 1. Then there's another cool effect. This is just from the transients that are perturbed within the kicker and the quad plates. So this is crazy, and Eric Swanson spent a long time figuring a lot of this out. But when you pulse the quads, they vibrate a little at a sort of mechanical natural frequency. And that vibrating metallic plate inside a field will generate a little bit of a field itself. And we worked a long time to build special instrumentation to measure this. And so we have a pretty big systematic on this. It's the largest systematic of all of them for a very small net effect. And it's simply because we're not finished yet doing all of the mapping. We had to do a special thing. We'll do that this summer. So this will go down. This was the original elephant, by the way. And the last one is just the normal thing. You know, eddy currents. So if you make a big magnetic pulse in the kicker, then you're going to get eddy currents that linger. Here's a map of these that Dave Kawal and his group at Massachusetts developed, this particular way of doing a magnetometer. So you put in a magnetometer, a Faraday magnetometer, so when you put polarized light in, and it turns based on the field and comes back up. So you're looking for the rotation of that light in a special device. And they were finally able to measure this. There were many magnetometers built, but it's super hard because it's tiny. We're talking milligauss on top of a big field. And so that's a pretty reasonably under control one as well. So all of those things you put together, we all had to read all that stuff. We had to digest all that stuff. We had to decide, was it right? And we had to vote on this. It went through a long time. There was an envelope here. There was an envelope that Chris has got at Fermilab. We both had the same numbers. We typed them into a spreadsheet that our Italian colleague Alberto had put together, and immediately get the answer. So this was the answer you have maybe seen, that the new number is here. It agrees with the old Brookhaven number. That's the most strong takeaway statement. If you look at the values that we have, all those corrections I said are about a total of 544 part per billion. The uncertainty, the net uncertainty is 462 part per billion. And notice that it's almost all statistical, which is great. Many of these are under control. The large ones that I mentioned to you, the two elephants, will go almost completely away, which is great. So we're going to be in good budget for that. And so I could stop at this point if you want. I don't know where we are in time. We're close. I could tell you a little bit what this might mean, but it's certainly very briefly, here we are all in ELBA now. It basically is a strong motivation for us to push the end of this measurement. There's lots of other precision muon physics experiments out there whose stock just went up. Other precision experiments, lepton flavor universality, beta decays, molar, EDMs, BK, these are all up. And the theorists need no motivation because there's already 41 citations in 2 days to the PhysRev letter. So it's hard for me to sort of summarize the thematic nature of that. You know, I'll answer this about what it might mean in the question period if you wish, but I'd like to just finish here. This is the first result after 10 years of work. We have a lot to do. We've confirmed Brookhaven. That didn't look like a fluke, which was getting me nervous because, well, it got all of us nervous. There were only about 10 of us from that old experiment out of 200, by the way. And it increases the tension. We're up to about, 4.2 standard deviations away from the standard model version. I want to also make a special shout out right now because about 11 years ago or so, there were people here in the University of Washington that somehow took a chance and to drag our group out here, Peter, myself, and our students and postdocs. And I just want to thank you for doing that because it's been a spectacular experience to be able to be here, to develop our group and our work here, and of course, to live in this incredible city. So thank you very much.
Okay, very nicely done, David. Thank you. The questions, let's see. People can raise their hand or they can type it in the chat. I can read your question for you. Any questions to start us off? Miguel, please go ahead.
So from having a few of your students and sitting on various exams, I know about your kind of tiered unblinding process, which is the most sophisticated unblinding I've seen. And so I wanted to give you an opportunity to talk a little bit about that because I think it's super cool. But then the other one was getting towards the end here with that kind of thing. When you finally did your final unblinding, were you anxious? Were you confident because you'd done things? Had you just been beaten into submission?
I will tell you, Miguel, that this particular individual that you're looking at right now was terrified at some level for reasons that are different. Everyone was terrified for different reasons, but I started to feel the responsibility of dragging a bunch of people out here to the University of Washington, getting a lot of money, having a lot of you think we're okay people, having students buy into this. It was, I didn't care where the number was. I just wanted it to be on the plot, So, so we had lots of discussions. I would say my colleague Chris Pauly, who is our spokes now, he was sure we were going to land here because he just believed his thesis was this number, so he was damn sure he did his thesis right. So he was more sure, and I was beginning to be unsure, and everyone had different emotions, I would say, at this point. And when it showed up there, the feeling that this is really going to be fun took over. And nice thing, I love the fact that it ended up here. Of all, this is, you can bounce anywhere, that. But it's nice, if it was way over here, then maybe we would lose a little bit of momentum in the balloon. Right now, we're pretty darn motivated to, finish that next batch of data and the next batch of data and so on.
Very nice. Here's a question from the chat from John Howell. So Dave, what factors cause the magnetic field to have its longer term drift over the course of days?
Temperature. The completely driven thing was the fact that the Hall was ideally supposed to be of the order of 1 degree C kind of tolerance, but this is Chicago. The heat had, the heater hadn't come on in a year and a half, all the way through Chicago winter, because we had about 5 times as much equipment in there than we budgeted that was constantly heating it. So we couldn't keep that Hall cool as it got into the spring. And so what happens to a clamshell magnet like that is it's going to open and close like that, and that's going to change the field in here, and it's going to change the multiples in there. So the magnetic field team really had a ton of work to do that. You should see what it looks like now, just butter flat. But also our detectors were being basically cooled from the temperature of the room, and our detectors are very sensitive to gain. There's silicon photomultipliers. So the field was much more important than our detectors, but that's where the laser system tracked up and down the same thing. So you could basically see all of that happening at once. That is much better shape than it was before, whoever was asking.
Very nice, thanks. Second question from the chat, actually it mirrors my my own question. So what are some of the new physics that can most easily explain this discrepancy between the experiment and the standard model right now?
This is one of our colleagues sent this to us, and I'll give you 2 answers quickly for it. First of all, real fast, what works and what doesn't work right now. There are some things like 2 Higgs doublet models, leptoquarks, the expanded, minimal supersymmetric model with all its parameters, and some no-name models, as they call them, some very specific odd things. But some stuff that doesn't work is constrained MSSM, minimal supersymmetry. These are all ruled out by the LHC, and it's very hard. But the basic thing that I go to is a more generic thing. Dominic has put, and his collaborators have about a 100-page paper that's been put on the archive that they've been working on long before this number came out. They just waited to put it up. But essentially, the deviation is larger than the standard model electroweak contribution. So if you think about that, the electroweak contribution, sort of 100 GeV kind of stuff, this is a bigger thing than that. And it's not easy to imagine a bigger loop than that without some kind of enhancement factors. And the anomaly is this loop-induced CP and flavor-conserving chirality flipping part. That's what anomalous is. It's a chirality flipping part. So you have to go in and figure out what can make that happen. Stuff that couples to the physics of the muon mass itself, for example, does that kind of diagrams. So basically, the beyond the standard model scenarios can give this, but it's getting very tough because typically one is forced down here into non-traditional parameter regions. So it's beginning to look as ugly. In other words, new physics would be as ugly as the standard model itself, which itself is ugly.
Very nice. Then we have 2 more in the chat, and one from and then one from Henry. Let's see. So in the chat, VINC is asking, what does the size of this anomaly? I think the question is, what does the size of the anomaly look like in terms of how the muon is processing? Like maybe you can give a sense for the size of that anomaly, and then how do the positrons play a role? If you could touch on that.
What is specifically the anomaly related to the precession of muon in the accelerator, and how do the positrons play a role? Okay. Let's do the second one first. The positrons are encoding the spin. Where's the spin? So the positrons are collected, and that little oscillation spectrum is just telling you which way was the ensemble spinning on average at the time. So over time, you see it going around, and that's simply the positron spectrum, which is hitting the detectors with a modulated rate of a certain energy. So that's what they're doing. And then the anomaly, if the anomaly was 0, then the muon would not precess at all. The spin would be lined up with the momentum the whole time around and around. As the anomaly is larger, the spin, it goes faster. If the anomaly is small, it goes lesser. So we're just figuring out the rate of that difference is proportional to the anomaly, and that's encoded by the positrons.
Oops, I muted myself. Thanks. And then Alvaro had a question about how different the two experiments, FNL and...
That's a really good question, Alvaro. In fact, our collaboration since 6 or 8 months ago put together a little study group of the people who knew that experiment still, old timers, and we went through all of the systems. So generically, the recipe is the same. You could argue the magnet's the same, but a magnet is a magnet. I mean, it doesn't have any particular dynamic features to measure. The systems the kicker is different. The quads were differently pulsed, which gave us this disaster in the end of the day. And they're pulsed at a different rate. So the one worry was this problem with the elephant from the quadrupole pulsing problem. We calculated it through for Brookhaven, and it looked to be a pretty much not so much important issue. It would have been overlooked at Brookhaven. It wouldn't have been that was different. It would have been overlooked there. But we worked that out. And that seemed okay. The detectors and so on are all completely different. We sort of went through everything we could think of that would be tied together and realized that it just was really nothing. There was a common probe, absolute calibration probe we used. But we have other absolute calibration probes that are better to know that probe was still okay. So that sort of cancels out anyway. So at the end of the day, there was nothing that had to be done, but we went through a pretty good exercise. And the other important thing that we want to remind people is, in both cases, it's statistics that are the largest error.
Okay, and then Henry, you go ahead with your question.
Okay, thank you. First, David, this is an incredibly elegant and beautiful experiment. Congratulations to you and the entire team. My question is that on the day you announced on the 7th, there was a new paper from a lattice gauge group. As that seems to be has quite a bit of tension with the dispersive calculations as well as other lattice gauges. Is there anyone who's had a look at that? Is that just being dismissed, or is it something that one needs to take seriously?
I haven't seen that paper yet, Henry, or heard about it. Let me just say a couple things. First of all, for those not completely aware of that, it's gotten such a press because Nature timed the release of this just to make a little bit of a splash, I suppose, and so it now can be called that new lattice result. And it's made this BMW collaboration, and it's extraordinary work. I mean, if you actually look at this paper, this is really serious stuff. But all of these blue lines here represent the many lattice efforts that are sort of developing and trying to get the hadronic vacuum polarization term to be able to be done on a computer. And this one started off over here, and this is its 3rd iteration before it was published. So it finally ended up back here, but it's actually moved a lot during the time period. And I want to point out, it's the first of its kind that's at the sub% level, which is impressive, like 0.8% level. And it's very odd psychologically to me, because this is a calculation with a new tool pushing into a new level, and we're comparing it against decades of experimental work by many collaborations which have been scrutinized because these guys have been battling each other over cross sections and systematics. It's not like, and they're all done blinded, and they're experiments. There's not a dispersive calculation. There's cross sections, and then there's basically arithmetic. There's a very, you can add that up. It's not a calculation you're doing per se. And so it's pretty unusual when the physics community says, hey, there's 4 experiments over here, but let's take this new calculation and throw it. I thought it worked the other way around.
Yeah, no, I agree with you.
But I'm still excited for them. Let me just say, in case I am very excited by this, because in time, these blue lines are going to end up somewhere. They're all going to be working on this. They should be prioritized, and it's going to be added value.
Yeah, no, thank you, David. I share your comments. I share with you what you just told us. This is kind of what I'm thinking also.
Thanks, Henry.
Thanks, Henry. Let's go to Chelsea.
Hi, Dave. This is really exciting. I just wanted to ask, sorry if you answered this question already. So your statistics limited, does that mean you're going to run for longer, or do you have plans to inject more muons, or like what is the plan?
I turned this off. What is that lap? Start, stop, 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 stop. Ah! Threw it across the room. Did I show that plot? You asked about, our data. I did earlier. That's right. We've got run 2 under the belt. Run 3 was going beautifully until COVID hit. Run 4 started kind of December. It's been running continuously. I like to say, after all of this fun, I have shifts next week, which doesn't sound like fun to me. And we'll do run 5. And after that, it's going to depend on where we are. And some people talk about using negative muons. I'm not sure. We have to think a little bit, but we're definitely going to run all next year again. Can you get rid of that?
Okay. Thanks.
I can't. Nancy just came by to take my phone out and smash it for me. Yeah, so we're gonna be running a good bit more, and we'll be, the lag to analyze this data, Chelsea, is also kind of long. So each time you pass another milestone of precision, you run into another elephant of some sort. You think you know the recipe until you hit the data.
Yeah, I'm sure. Thanks.
Okay, any other final questions? Well, if not, let's wish David good luck on his elephant hunting, and well done.
Thanks, everybody. Really fun to give that talk here.
See you all next time.
Cheers.
Cheers.